Hello, this is software group 5 that is working on NeoScreen, which is a multimodal AI for detecting neonatal respiratory distress. My name is Mebu Tusime, and my group mate here with me is Abisha Paingana. So the roadmap for our presentation today is going to include introduction, related works, problem statement, methodology, results and analysis, limitations, etc. So our background, where this came up from. So when we were making our research, we found out that 47% of the deaths under 5 years old occur in the first 28 days of life, where this is the neonatal stage. And 98% of these deaths occur in low and middle income countries, which is alarming. And then respiratory distress is the third leading cause of these deaths. So the current gap is that there are great advances in medical AI, but there is none that is calibrated edge deployable system for neonatal respiratory triage in resource-constrained settings where a lot of these deaths are happening. Existing solutions require cloud connectivity, expensive hardware, or lack clinical interpretability, which makes the early detection difficult. Early detection of respiratory distress in newborns can reduce mortality by up to 40% with timely intervention. So these are some of the related works that we looked at as we're making our research. Zhang et al. Its limitations was it was pediatric only, had no neonate data. Sata et al. Was audio only and it had a small sample space. Im et al. Had a single modality, so it was working with one model type. Hugh et al. Had no clinical data. Electric Sheep Africa had no audio, it was synthetic data only. And Huang et al. Is rarely used in healthcare. So what is our problem statement? The clinical problem is that there is subjective assessment. So different clinical workers have different diagnoses, which is inconsistent. And then there's shortage of experts in this field. So they miss early signs that could have given hints to respiratory distress, and then delayed intervention for the sick neonates. And therefore, they are preventable deaths. But because there's a long time taken to work on them, they end up dying, which increases the mortality rate. And then the statistics we talked about earlier, whereby 47% of deaths under 5 are neonates, and then 98% of these deaths are in low and middle income countries, and respiratory distress is the third leading cause of these deaths. So what's our computational problem? We have tabular data, which is clinical variables, and then there's audio data that are respiratory sounds and audio input, but there is an imbalance whereby the respiratory distress cases are only 2.6% of the data set, which means it's imbalanced, and then there are unpaired sources. So there is no combination of synthetic and public audio. So the synthetic is alone, and then the audio data is alone. So our research questions include which acoustic features best characterize stridor and grunting in neonates? And then does multimodal fusion actually outperform the single modality models? And then which fusion strategy is optimal for edge deployment? Is it early, is it late, is it intermediate fusion? And then how can predictions be explained? Then our objectives, we hope to extract acoustic features, develop a multimodal pipeline, implement the late fusion ensemble, and then deploy the fused model. So these are our research contributions and outputs, and I'll hand over to my group mate, Abisha.
Thank you, Mebo. So what we are going to contribute based off the related works and what we identified as the research gap is we are going to have a novel late fusion approach, which is going to be the first of its kind for unpaired acoustic and clinical neonatal data. And then we have a comprehensive model evaluation based off the 8 models that were developed, that is CNN, long short-term memory, the extreme learning machine, the ResNet 18, XGBoost, convolutional neural network, graph neural network, and logistic regression. Then we also have a fused model that will be state-of-the-art with 100% accuracy deployed on Hugging Face, and dual attribution XAI based on SHARP for clinical features and GradCam for the mel-spectrograms, together with integrated gradients for cross-model attribution. And our methodology, this is what we are going to be looking at under our methodology, and that's starting from the two data sources, which is clinical data, which is synthetic with 30,000 records. We shall do pre-processing with imputation of missing values and encoding of categorical values, then extract 12 clinical features, which will be standardized, then model training, and from the clinical models, we chose the extreme learning machine model, and we trained it using random weights as well as pseudo inversion, and we shall evaluate it based on specific metrics, that is the accuracy, precision, recall, F1 score, and the area under the ROC curve. Then for the acoustic data, which had about 2,000 plus recordings, we pre-processed it using resampling, noise reduction, and segmentation, then extracted mel-spectrograms and normalized the extracted features, then trained the selected model, which was the convolutional neural network long short-term memory model. And we also did some focal loss to balance out the stridor class, which was imbalanced, and also evaluate it based on the same metrics as those in the clinical model. And then we shall have a late fusion ensemble, and finally evaluate it based on still the final accuracy, the fused F1 score, and the confusion matrix. And we shall also have the final output as a deployed model on Hugging Face. Then for our model architecture, we are looking at the two inputs, which is audio and clinical input. With audio, we have mel-spectrograms as our input, and with the clinical input, we are looking at the 12 standardized features. And we shall have the two models, which is the CNN-LSTM and the ELM models, and then have the audio predictions and the clinical predictions, which we shall then pass through the late fusion ensemble with that formula to have our risk threshold. And then we shall compare the final prediction using the risk threshold to see if the neonate is high risk or low risk based on whether the final prediction is above or below 0.5. Then for our dataset description and EDA, we used two datasets. That was the acoustic dataset, which was SPR sound, which had about 6,000 plus samples, and we did it on 6 classes, and we had about 33 features extracted with it. And then the clinical data set, which had about 30,000 records, and 3 burden scenarios, which has low, moderate, and high burden. And we had about 15 key plus features. So on the right, we look at the different visualizations from both data sets, such as the burden level, percentage, distribution of delivery mode by the burden level, correlation heat map, and then gestational age versus the respiratory rate. Then for the acoustic data set, some of the visualizations from the EDA were the wavelet scalogram comparisons between normal respiratory sound, a normal breath sound, and a wheeze. And then we also had the average amplitude in by age group. Then for our results and analysis from the exploratory data analysis, we ended up choosing our two best models, which we fused together. That was the clinical ELM and the audio CNN-LSTM. This was the performance. These were the metrics that we used to evaluate those two models, and also the formula that we used to get the validation area under curve versus the fusion weight, where our optimal weight was 0.3. And then we also had dual attribution, where we looked at the ELM plus the SHARP values to identify the hidden neuron contributions. Then we had the fusion of the integrated gradients for cross-modal attribution. And some of the limitations that we identified we had three main limitations. That is class imbalance, whereby with the clinical data set, we had only about 2.6% positive cases out of the 30,000 plus records. Then with the audio data set, we had only about 22 samples for the stridor class, which was one of the most important classes for NRD. Then the impact of this class imbalance was that models ended up coming out biased towards the majority class, and our countermeasure for this was using class weights and sample weights. Then the second limitation was unpaired modalities, where there was no patient overlap between the audio data and the clinical data, since we got them from different sources and there was no overlap between them. Then with this, we found that we could not just train them using the early or intermediate fusion, since here we would have a joint distribution hallucination with our models. So our countermeasure for this was late fusion only. And then for the third limitation, which is the domain shift, because we found that the audio data that we used was actually specific to the pediatric domain, which was from 1 month all the way to 18 years, unlike the neonatal domain that we wanted. And then for the clinical data, it was actually synthetic and might not generalize to real neonates. So our countermeasure for this is to use transfer learning once the models are done being trained. Then our conclusion and future works. Here I will hand over to my partner to take us through.
Thank you, Abisha. So our conclusion and future works, we have carried out training and validation of the 8 models that were mentioned earlier. Then late fusion, where we used naive-based ensemble fusion, which is late fusion. Edge optimization, we have deployed the model to Hugging Face spaces. And then we hope to carry out clinical validation, which when we get neonatal data. So some of the references we worked with are listed here: Zhang et al., Huang et al., Electric Sheep Africa, Sata et al., Im et al., and so on. That was our presentation. Thank you. Every granting baby deserves a chance. Once again, my name is Mebo Tusime, and my group mate is Abisha Baingana. Thank you.